Hello friends, in today's lecture we shall be talking about the Karnaugh maps. A Karnaugh map provides a systematic method for simplifying Boolean expressions and if properly used will produce the simplest SOP and POS expression possible known as the minimum expression. As you have seen, the effectiveness of algebraic simplification depends on your familiarity with all the laws, rules and theorems of Boolean algebra and your ability to apply them. The Karnaugh map, on the other hand, provides a cookbook method for simplification. A Karnaugh map is similar to a truth table because it presents all of the possible values of input variables and the resulting output for each value. Instead of being organized into columns and rows like a truth table, the Karnaugh map is an array of cells in which each cell represents a binary value of the input variable. The cells are arranged in a way so that simplification of a given expression is simply a matter of properly grouping the cells. Karnaugh maps can be used for expressions with 2, 3, 4 and 5 variables, but we will discuss only 3 variable and 4 variable situations to illustrate the principles. The number of cells in a Karnaugh map is equal to the total number of possible input variable combinations as is the number of rows in a truth table. For 3 variables, the number of cells is 8, which is 2 to the power 3, and for 4 variables, the number of cells is 2 to the power 4 and is equal to 16. The 3 variable Karnaugh map. The 3 variable Karnaugh map is an array of 8 cells as shown in part A of figure. In this case, A, B and C are used for the variables, although other letters could be used. Binary values of A and B are along the left side and the values of C are across the top. The values of a given cell is the binary value of A and B at the left in the same row combined with the value of C at the top in the same column. For example, the cell in the upper left corner has a binary value of 000 and the cell in the lower right corner has a binary value of 101. Part B of figure shows the standard product terms which are represented by each cell in the Karnaugh map. The 4 variable Karnaugh map. The 4 variable Karnaugh map is an array of 16 cells as shown in figure A. Binary values of A and B are along the left side and the values of C and D are across the top. The value of a given cell is the binary values of A and B at the left in the same row combined with the binary value of C and D at the top in the same column. For example, the cell in the upper right corner has a binary value of 0010 and the cell in the lower right corner has a binary value of 1010. Part B of figure shows the standard product terms which are represented by each cell in the 4 variable Karnaugh map. Cell adjacency. The cells in a Karnaugh map are arranged so that there is only a single variable change between adjacent cells. Adjacency is defined by a single variable change. In the 3 variable map, the 010 cell is adjacent to the 000 cell, the 011 cell and the 110 cell. The 010 cell is not adjacent to the 001 cell, the 111 cell or the 101 cell. Physically, each cell is adjacent to the cells that are immediately next to it on any of its four sides. A cell is not adjacent to the cells that diagonally touch any of its corners. Also, the cells in the top row are adjacent to the corresponding cells in the bottom row, and the cells in the outer left column are adjacent to the corresponding cells in the outer right column. This is called wraparound adjacency, because you can think of a map as wrapping around from top to bottom to form a cylinder, or from left to right to form a cylinder. This figure here illustrates the cell adjacencies with a 4 variable map, although the same rules for adjacency apply to Karnaugh maps with any number of cells. Mapping a standard SOP expression. As discussed in the last section, the Karnaugh map is used for simplifying Boolean expressions to their minimum form. A minimized SOP expression contains the fewest possible terms with the fewest possible variables per term. Generally, a minimum SOP expression can be implemented with fewer logic gates than a standard expression. For an SOP expression in standard form, a 1 is placed on the Karnaugh map for each product term in the expression. Each 1 is placed in a cell corresponding to the value of a product term. For example, for the product term A B bar C, a 1 goes in the 101 cell on a 3 variable map. When a SOP expression is completely mapped, the number of ones on the Karnaugh map equal to the number of product terms in the standard SOP expression. The cells that do not have a 1 are the cells for which the expression is 0. Usually, when working with SOP expressions, the zeros are left off the map. The following steps and the illustration in figure shows the mapping process. Step 1. Determine the binary value of each product term in the standard SOP expression. After some practice, you can usually do the evaluation of terms mentally. Step 2. As each product term is evaluated, place a 1 on the Karnaugh map in the cell having the same value as the product term. A Boolean expression must first be in the standard form before you use a Karnaugh map. If an expression is not in standard form, then it must be converted to standard form by the procedure covered in earlier discussion or by numerical expansion. Since an expression should be evaluated before mapping anyway, numerical expansion is probably the most efficient approach. Numerical expansion of a non-standard product term. Recall that a non-standard product term has one or more missing variables. For example, assume that one of the product terms in a certain 3 variable SOP expression is A B bar. This term can be expanded numerically to standard form as follows. First, write the binary value of the 2 variables and attach a 0 for the missing variable C bar. Next, write the binary value of the 2 variables and attach a 1 for the missing variable c. The two resulting binary numbers are the values of the standard SOP terms. Karnaugh map simplification of SOP expressions. The process that results in an expression containing the fewest possible terms with the fewest possible variables is called minimization. After an SOP expression has been mapped, a minimum SOP expression is obtained by grouping the ones and determining the minimum SOP expression from the map. You can group ones on the Karnaugh map according to the following rules by enclosing those adjacent cells containing ones. The goal is to maximize the size of the groups and to minimize the number of groups. A group must contain either 1, 2, 4, 8 or 16 cells, which are all powers of 2. In case of a 3 variable map, 8 cells is the maximum group, which is 2 to the power 3. Each cell in a group must be adjacent to one or more cells in that same group, but all cells in the group do not have to be adjacent to each other. Always include the largest possible number of ones in a group in accordance with rule 1. Each one on the map must be included in at least one group. The ones already in a group can be included in another group as long as the overlapping groups include non-common ones. Determining the minimum SOP expression for the map. When all the ones representing the standard product terms in an expression are properly mapped and grouped, the process of determining the resulting minimum SOP expression begins. The following rules are applied to find the minimum product terms and the minimum SOP expression. Group the cells that have ones. Each group of cells containing ones create one product term composed of all variables that occur in only one form within the group. Variables that occur both uncomplemented and complemented within the group are eliminated. These are called contradictory variables. Determine the minimum product term for each group. For a 3 variable map, a 1 cell group yields a 3 variable product term. A 2 cell group yields a 2 variable product term. A 4 cell group yields a 1 variable term. An 8 cell group yields a value of 1 for the expression. For a 4 variable map, a 1 cell group yields a 4 variable product term. A 2 cell group yields a 3 variable product term. A 4 cell group yields a 2 variable product term. An 8 cell group yields a 1 variable term. A 16 cell group yields a value of 1 for expression. When all the minimum product terms are derived from the Karnaugh map, they are summed to form the minimum SOP expression. Mapping directly from a truth table. You have seen how to map a Boolean expression. Now you will learn how to go directly from a truth table to a Karnaugh map. Recall that a truth table gives the output of a Boolean expression for all possible input variable combinations. An example of Boolean expression and its truth table representation is shown in figure. Notice in the truth table that the output x is 1 for 4 different input variable combinations. The ones in the output column of the truth table are mapped directly onto a Karnaugh map into the cells corresponding to the values of the associated input variable combinations. Here you can see that the Boolean expression, the truth table and the Karnaugh map are simply different ways to represent a logic function. Mapping a standard POS expression. In the last section, we discussed the minimization of an SOP expression using a Karnaugh map. In this section, we will focus on POS expressions. The approaches are much the same except that with POS expressions, zeros representing the standard sum terms are placed on the Karnaugh map instead of ones. For a POS expression in standard form, a 0 is placed on the Karnaugh map for each sum term in the expression. Each 0 is placed in a cell corresponding to the value of a sum term. For example, for the sum term A plus B bar plus C, a 0 goes in the 010 cell on a 3 variable map. When a POS expression is completely mapped, the number of zeros on the Karnaugh map equal to the number of sum terms in the standard POS expression. The cells that do not have a 0 are the cells for which the expression is 1. Usually, when working with POS expressions, the ones are left off. The following steps and illustration in figure shows the mapping process. Step 1. Determine the binary value of each sum term in the standard POS expression. This is the binary value that makes the term equal to 0. Step 2. As each term is evaluated, place a 0 on the Karnaugh map in the corresponding cell. Karnaugh map simplification of POS expressions. The process for minimizing a POS expression is basically the same as for an SOP expression, except that you group zeros to produce minimum sum terms instead of grouping ones to produce minimum product terms. You can group zeros on the Karnaugh map according to the following rules by enclosing those adjacent cells containing zeros. The goal is to maximize the size of the groups and to minimize the number of groups. A group must contain either 1, 2, 4, 8 or 16 cells, which are all powers of 2. In the case of a 3 variable map, 8 cells is the maximum group, that is 2 to the power 3. Each cell in a group must be adjacent to one or more cells in the same group, but all cells in the group do not have to be adjacent to each other. Always include the largest possible number of zeros in the group in accordance with rule 1. Each 0 on the map must be included in at least one group. The zeros already in the group can be included in another group as long as the overlapping groups include non-common zeros. Converting between POS and SOP using the Karnaugh map. When a POS expression is mapped, it can easily be converted to the equivalent SOP form directly from the Karnaugh map. Also, given a mapped SOP expression, an equivalent POS expression can be derived directly from the map. This provides a good way to compare both minimum forms of an expression to determine if one of them can be implemented with fewer gates than the other. For a POS expression, all the cells that do not contain zeros contain ones, from which the SOP expression is derived. Likewise, for an SOP expression, all the cells that do not contain ones, contain zeros, from which the POS expression is derived. So, that brings us to the end of our discussion on Boolean algebra. In this lecture, we discussed the 3 and 4 variable Karnaugh maps, the mapping of SOP and POS expressions, Karnaugh map simplification, and finally mapping directly from truth table. So, friends, see you in the next lecture. Thank you very much.